Okay, hello Angelica. This is Ethan here. I'm going to go over the last question we missed yesterday because we didn't have enough time. However, though, it's fairly simple. And if you'll remember our work from yesterday when we talked about one-tailed hypothesis, excuse me, one-tailed hypothesis tests for proportions, this one's much simpler because now we're just doing two tails. So here's our question. We're going to use the classical method. The editor of a newspaper has written that 25% of university students at the paper's circulation area read newspapers daily. A random sample of 200 of these university students shows that 45 of them are daily readers of the newspaper. At the 0.05 level of significance, is the editor's statement likely to be true? Okay, so we're doing the classical method. So step one is always what is our hypotheses. So our null and our alternative. Our null is that the proportion is equal to 25, or sorry, 0.25. And the null is that it's not going to be equal to 0.25. And looking at this step here, you can tell it's going to be two-tailed because there is a do not equals. There is going to be one-tailed if there's a greater than or less than symbol right there. In this case, there isn't, so it's going to be two-tailed. Step two is to determine the level of significance. In this case, it always pretty much tells us 0.05. Step three, remember, this is kind of where it starts to get a little bit weird. We have to test if the data sample is large enough so that we can use the normal distribution. And if you'll remember, we have these two rules. The number times the proportion of the sample should be greater than 5, and the number in the sample times 1 minus the sample proportion should also be greater than 5. So let's calculate these two values and see if they're both greater than 5. So it looks like the number in this case, n, we'll change colors right there. N is equal to 200, and the sample proportion is going to be equal to it's going to be equal to 45 over 200. And if you grab your calculator, that should be 0.225. 225. Perfect. So let's plug it into our calculations up here. So that's 200 times 0.225, which is going to be equal to 45, which is greater than 5. So that test is passed. Down here, 200 times 1 minus 0.225. That's going to be, well, 200 times 1 minus. In the calculator here, you're going to get 120 or 55. That is greater than 5. So yes, this one also passed. Since both since both tests are passed, we're going to use the normal distribution. Otherwise, we'd have to use the t-distribution if one or both of these failed. In this case, they both passed, so we're going to use the normal distribution. Great, so that's step 3. Okay, so step 4 is we got to figure out our critical z values. So that's going to involve us. Oh, maybe I should. Step 4. That's going to mean we're going to draw out our normal distribution. Oh, there we go. And center it a little bit better. And we know the middle is going to be 0. And looking back at our level of significance here, our error level, that is a 0.05. And since this is a two-tailed test, because we can look at the hypothesis here, we know that we're going to have to evenly split that error onto both sides of the normal distribution. So both of these are going to be red areas, rejection regions, and each of them is going to be exactly half of the total error. So each side is going to be 0.025. Now we're interested in the z values right here. So z and negative z. We want to know what these are so we can make a rule. We want to figure out the z-score here related to this the area to the left of 0.025. So what that means is we're going to go to the table here. We're going to look for the number closest to 0.025. And if you look close, you can see right here at the intersection of negative 1.96. You can see that is as close as we get. So 1.96 is our z value. So if we come back down here, we can say this is negative 1.96, and therefore the positive is going to be positive 1.96. So our rule is going to be that step 5, excuse me. The rule is we are going to don't reject if z is within the bounds of 9.6, a negative 9.6 and positive 9.6. Otherwise, we're going to reject the null hypothesis. Perfect. That's step 5. I am going to maybe squeeze this in here, make this a little bit smaller so we got room. Step 6 is we got to find the test statistic. So we are going to figure out what our z value is. And remember that formula gets a little weird. It's going to be the, excuse me, it's going to be the sample proportion minus the null proportion over top of the standard deviation of the proportion of the sample. So we can look at our question. Actually, I don't think there's a line up there. We can look at our question. We figured out already what the sample proportion is, and that was our 0.225 minus 0.25. It's what the stated in the null hypothesis. And if you remember, the standard deviation of the proportion is a little bit more complicated. So we have to write a separate formula here. And that is going to be the square root of the null proportion times the 1 minus the null proportion all over n. So fill in those values. We're going to get, this is 0.25 times 0.75 all over the sample, or the number, which is 200. Amazing. You're going to throw that in your calculator. Oh, maybe. Throw that in the calculator. And you should get 0.03, a couple more decimal places, 0.6 as your standard deviation of the proportion. So we're just going to then plug this in up here, 0.0306. And now we have all the pieces to the puzzle, and we can calculate the z statistic. So throwing that in my calculator here, I have gotten negative 0.81699 something. Goes on. Now step 7, I'll do it over here since I'm running out of room. Step 7 is finally to summarize and write our conclusion. And so looking at our test statistic and looking at our rule, you can see that this passes. We're not going to reject it because this z is in between these two, so that's good. And it's not in the rejection region, so we are going to not reject or accept the null hypothesis, since this number, I'll copy it, is within the bounds of this up here. We'll copy this and make sure right at the 0.05 level of significance. Awesome. That's how you answer that question there. Let me know if that makes sense and if you have any additional questions.